Blueprint for Mars Colonization, breakdown of NASA's $30 billion budget allocation and 5-phase implementation strategy by 2032. Introduction. NASA's ambitious plan for Mars colonization with an allocation of approximately $30 billion aims to establish a sustainable human presence on the red planet by 2032. This extensive blueprint outlines a comprehensive 5-phase strategy that addresses the myriad challenges posed by Mars' environment and emphasizes innovative technological solutions. Budget allocation and phases. NASA's budget is structured around 5 distinct phases, each critical to the overall vision of Mars colonization. The phases are as follows. 1. Preliminary unmanned missions 2024 to 2026. Objective: conduct resource assessment and technology testing. Activities: deploy rovers and landers to analyze Martian soil atmosphere and potential in-situ resources. Focus: establish the feasibility of using local materials for construction and life support systems. 2. Short-term manned missions 2027 to 2029. Objective: test life support systems and establish initial infrastructure. Activities: send crewed missions to Mars for a duration of several months to evaluate human factors and operational capabilities. Focus: gather data on the physiological effects of long-term space travel and habitation in reduced gravity. 3. Infrastructure development 2030 to 2032. Objective: build sustainable settlements utilizing Martian resources. Activities: construct habitats, laboratories, and agricultural facilities using Martian concrete and other local materials. Focus: develop advanced life support systems that can recycle air, water, and waste. 4. Expansion of human presence 2032 and beyond. Objective: increase the number of settlers and enhance the colony's capabilities. Activities: establish additional habitats and research facilities and create a permanent human settlement. Focus: implement in-situ resource utilization ISRU techniques to produce fuel, water, and food locally. 5. Long-term sustainability and self-sufficiency 2035 and beyond. Objective: achieve a self-sustaining human presence on Mars. Activities: develop advanced agricultural practices including aeroponics and algae bioreactors for food production. Focus: ensure the colony can thrive independently of Earth support, addressing psychological and physiological health needs of the inhabitants. Challenges and solutions. Radiation exposure. One of the most significant challenges is radiation exposure, which astronauts may experience at levels of approximately 0.66 sieverts during round trips. Solution: development of effective radiation shielding methods such as constructing habitats underground or utilizing Martian regolith as a protective barrier. Environmental conditions. Mars presents extreme temperatures and a thin atmosphere, complicating life support systems. Solution: innovative life support systems that can recycle air and water, along with the development of habitats that can maintain stable internal conditions against external extremes. Resource utilization. To minimize the need for Earth-based resupply missions. Efficient use of Martian resources is essential. Solution: in-situ resource utilization ISRU technologies that enable the extraction of water from the subsurface and the production of fuel and construction materials directly on Mars. Economic viability. A cost-benefit analysis indicates that ISRU could significantly reduce dependence on supplies from Earth, making the colonization effort more economically viable. Reusable rocket technology, emphasized as a means to lower launch costs and increase mission frequency, enhancing the overall feasibility of sustained missions to Mars. Human factors. The psychological and physiological impacts of long-term space habitation are crucial considerations. Focus areas: addressing the effects of reduced gravity isolation and the need for social interaction among crew members. Psychological support systems and recreational activities will be integral to maintaining crew well-being. Timeline of events 2024 to 2026. Conduct preliminary unmanned missions for resource assessment and technology testing. 2027 to 2029. Execute short-term manned missions to test life support systems and establish initial infrastructure. 2030 to 2032. Focus on developing sustainable settlements and expanding human presence on Mars. 2035 and beyond. Aim for long-term sustainability and self-sufficiency of the Martian colony. Conclusion. NASA's comprehensive strategy for Mars colonization reflects a multifaceted approach combining technological innovation with careful planning. The phased implementation strategy emphasizes the importance of addressing the unique challenges posed by Mars while ensuring the well-being of astronauts. As researchers, policymakers, and stakeholders engage with this blueprint, ongoing advancements in technology and life support systems will be critical to realizing the vision of a human colony on Mars. References 1. NASA's Mars Future Plan, NASA website eps//science.nasa.gov/resource/the Mars Future Plan/ 2. Newcart Florian. Towards Sustainable Horizons, a comprehensive blueprint for Mars colonization. Helion 2024. Harvard ADS https://ui.adzabs.harvard.edu/abs/2024 Healy 1026180n/abstract. This report synthesizes various sources and outlines the critical components of NASA's strategy to achieve a human presence on Mars by 2032, focusing on technological innovation, economic viability, and human factors essential for the success of such an ambitious endeavor. NASA's blueprint for Mars colonization, with a budget of around $30 billion, comprises a five-phase strategy intended to establish a human presence on Mars by 2032. While the plan appears straightforward, several counterintuitive aspects stand out when examining the details of this ambitious initiative. 1. Budget allocation versus expected costs. The $30 billion budget may seem substantial, yet some experts argue that it is relatively modest compared to the costs of similar historic space missions. For instance, the Apollo program cost over $150 billion in today's dollars. The counterintuitive realization is that despite advancements in technology and a better understanding of the Martian environment, the budget for Mars colonization remains lower than expected based on historical precedents. This raises questions about the adequacy of the funding for the complex challenges ahead. 2. Phased approach and timeframe. The five-phase implementation strategy intended to span from 2024 to 2032 suggests a rapid progression from unmanned to manned missions. Counterintuitively, the timeline may be overly optimistic given the history of space exploration where delays are common, while NASA aims for a swift transition. Historical data indicates that the development of new technologies and overcoming unexpected challenges often results in extended timelines. The expectation of a successful transition to sustainable settlements by 2032 seems ambitious considering these historical precedents. 3. Human factors and mental health. The psychological and physiological impacts of long-duration space travel are critical considerations. Interestingly, while NASA acknowledges these factors, the proposed solutions may not adequately address the complexity of human psychology in extreme isolation. The counterintuitive aspect here is that despite sophisticated life support systems and planning, the unpredictable nature of human behavior under stress could lead to significant challenges that are not fully accounted for in the current strategy. 4. Resource utilization and dependency. In-situ resource utilization (ISRU) is highlighted as a cornerstone of the colonization strategy, aiming to reduce reliance on Earth-based supplies. However, the counterintuitive reality is that the technologies required to effectively utilize Martian resources, such as extracting water from regolith or creating fuel from local materials, are still largely theoretical and untested in the Martian environment. This reliance on unproven technologies raises concerns about the feasibility of achieving true self-sufficiency on Mars, contradicting the optimistic projections. 5. Technological innovations and reliability. The plan emphasizes innovative technologies such as Martian concrete and advanced agricultural systems. However, the counterintuitive challenge lies in the fact that many of these technologies are at experimental stages and may face unforeseen complications when deployed in the harsh Martian environment. For example, while aeroponics and algae bioreactors present promising solutions for food production, their effectiveness under Martian conditions remains uncertain, highlighting a gap between theoretical innovation and practical application. 6. Economic viability and launch costs. Although the use of reusable rocket technology is touted as a way to lower costs and increase mission frequency, the counterintuitive possibility is that the initial investments in developing and deploying these technologies could be prohibitively high. The assumption that reusability will lead to significant cost savings does not account for potential technical failures, maintenance needs, and the complexities of operating in deep space, which may offset any expected savings. 7. Environmental challenges underestimated. While the blueprint outlines the extreme conditions on Mars, such as radiation and temperature variations, there may be an underestimation of the cumulative effects these factors will have on human health and equipment longevity. The counterintuitive aspect is that even with advanced shielding and habitat designs, the real-world implications of prolonged exposure to Martian conditions could exceed current models, potentially impacting the viability of long-term colonization. 8. Community and social structures. The strategy primarily focuses on technological and logistical aspects, potentially neglecting the importance of social structures and community dynamics in a Mars colony. Counterintuitively, without a well-thought-out plan for fostering community interpersonal relationships and social support systems, the mission could face significant hurdles related to teamwork and collaboration among crew members, which are critical for mission success. 9. Long-term sustainability versus short-term goals. The emphasis on establishing a human presence by 2032 may overshadow the need for long-term sustainability. The counterintuitive insight is that immediate goals might lead to shortcuts in planning that neglect the necessity of creating a resilient, self-sustaining ecosystem on Mars. This could result in colonies that are not truly sustainable and require continuous support from Earth, contradicting the foundational premise of self-sufficiency. 10. Public perception and political support. The public and political support for space exploration initiatives can be fickle, often influenced by immediate societal issues. The counterintuitive realization is that while the excitement about Mars colonization is high now, future political or economic shifts could lead to funding cuts or changes in priorities that jeopardize the entire endeavor. This unpredictability must be considered in the planning stages to ensure that the initiative can withstand fluctuations in support. In conclusion, NASA's blueprint for Mars colonization presents an ambitious and multifaceted strategy. However, the counterintuitive insights regarding budgetary constraints, technological reliability, human factors, and sustainability highlight the complexities and unpredictabilities of such an endeavor. These aspects underscore the necessity for a cautious and adaptable approach to ensure that the goal of establishing a human presence on Mars can be achieved effectively and sustainably. Important content overlooked in NASA's blueprint for Mars colonization. While the general outlines of NASA's plan for Mars colonization have garnered attention, several crucial aspects may not receive the emphasis they deserve. These elements are significant not only for the success of the mission but also for the broader implications of space exploration and human adaptability in extraterrestrial environments. 1. In-situ resource utilization ISRU. Many discussions around Mars colonization focus on technological advancements and human factors, but ISRU's profound implications are often underappreciated. The ability to utilize Martian resources, such as extracting water from the soil, producing oxygen from CO2 in the atmosphere, and creating fuel from local materials can radically shift the economic viability of long-term missions. This reduces the dependency on Earth for supplies, thus enabling more sustainable growth on Mars. Significance: by leveraging local resources, the mission can transition from a temporary outpost to a self-sustaining colony. This shift could set a precedent for future space missions, fundamentally altering how humanity approaches extraterrestrial exploration and settlement. 2. Psychological and physiological effects. While the blueprint acknowledges the psychological and physiological challenges of long-term space habitation, the depth of research and strategies to mitigate these issues often go unnoticed. The effects of isolation, confinement, and the reduced gravity environment on mental health are critical to ensuring astronaut well-being and mission success. Significance: addressing these human factors is not just about ensuring operational efficiency, it is about enhancing the resilience of astronauts and supporting their ability to perform under pressure. Developing robust mental health protocols could pave the way for future missions not only to Mars but also to distant destinations like Europa or beyond. 3. Technological innovation beyond infrastructure. The report focuses heavily on infrastructure development, such as Martian concrete and life support systems, but overlooks the potential for radical innovations in propulsion and transportation technologies. Concepts like solar sail propulsion and advanced robotics could revolutionize how we approach interplanetary travel and logistics. Significance: investing in diverse technological innovations can create a more flexible and efficient approach to colonization. These advancements could also have applications on Earth, leading to innovations in renewable energy and automated systems, thus benefiting humanity beyond the context of Mars. 4. Timeline and milestones. Though the timeline is presented, the specific milestones within each phase tend to be vague or understated. For instance, the transition from unmanned missions to manned missions needs clear metrics for success and failure. Significance: establishing transparent milestones allows for accountability and adaptability in the mission planning process. This can help in securing funding and public support, as stakeholders can see tangible progress and reassess strategies based on real outcomes. 5. Cultural and ethical considerations. The cultural implications of colonizing another planet are rarely discussed. The ethical considerations surrounding the potential contamination of Martian environments, the implications of claiming territory, and the responsibilities humans might have toward any existing Martian life forms if they exist are critical conversations that need more attention. Significance: as humanity takes steps toward colonization, engaging in ethical debates becomes imperative. This not only shapes how missions are conducted but also how future generations view their role as stewards of other worlds. 6. Collaborative international efforts. The blueprint predominantly reflects NASA's vision, but the potential for international collaboration is understated. Involving global partners could lead to shared resources, knowledge, and technology, enriching the colonization process. Significance: collaborative efforts can lower costs, enhance technological innovation, and foster peace through shared goals in space exploration. As we venture into the cosmos, fostering a spirit of cooperation may be essential for the long-term sustainability of human presence beyond Earth. 7. Long-term economic models. The emphasis on economic viability through ISRU is critical. Yet the report could benefit from a more detailed examination of long-term economic models that consider not just costs but also potential benefits of Mars colonization. Significance: understanding the economic ramifications of establishing a colony on Mars can motivate investment and interest from private sectors, thus accelerating technological advancements and mission timelines. Conclusion: NASA's blueprint for Mars colonization is a groundbreaking initiative that presents numerous challenges and opportunities. However, by honing in on the overlooked aspects such as in-situ resource utilization, psychological impacts, technological innovations, ethical considerations, and international collaboration, we can develop a more robust and comprehensive strategy for this monumental endeavor. Recognizing these nuances is vital not only for the success of the Mars colonization mission but also for the future of human exploration in the cosmos. 1. Comprehensive 5-phase strategy. NASA's approach to Mars colonization outlines a structured 5-phase strategy with a budget of approximately $30 billion. Starting with unmanned missions for resource assessment, the plan progresses to manned missions and aims for sustainable human presence by 2032. This phased methodology is crucial for gathering essential data, testing technologies, and gradually establishing the necessary infrastructure for long-term habitation. 2. Innovative technological solutions. The plan emphasizes the need for cutting-edge technologies to address Mars' challenging environment. Key innovations include the development of Martian concrete using sulfur, advanced life support systems like aeroponics and algae bioreactors, and effective radiation shielding to protect astronauts from harmful exposure. These technological advancements are critical in ensuring the feasibility and sustainability of a Mars colony. 3. Economic viability through resource utilization. A major focus is placed on in-situ resource utilization (ISRU), which involves using Martian materials to support colonization efforts. This strategy could significantly reduce dependence on Earth-based supplies and lower costs associated with launching materials from Earth. The use of reusable rocket technology is highlighted as a way to enhance mission frequency and reduce launch expenses, making the colonization effort more economically viable. For addressing human factors for long-term habitation, the psychological and physiological impacts of long-term space habitation are critical components of the colonization plan. Addressing issues such as isolation, reduced gravity effects, and mental health is essential for ensuring the well-being of astronauts. This includes developing support systems and strategies to mitigate the challenges posed by extended stays on Mars, thus enhancing the likelihood of successful colonization. 1. The Apollo Program 1961–1972. NASA's Apollo program was a landmark achievement in space exploration, culminating in the first successful manned moon landing in 1969. The program had a budget of approximately $25.4 billion, equivalent to over $150 billion today, and unfolded in multiple phases including unmanned missions like Apollo 4 and manned missions such as Apollo 11. The program faced significant challenges including the dangers of space travel, the need for advanced life support systems, and the psychological impacts of long-duration missions. Innovations in technology such as the lunar module and advances in communication played a crucial role in its success. The Apollo program set a precedent for human spaceflight and laid the groundwork for future exploration, including potential missions to Mars. 2. The International Space Station 1998–present. The ISS represents a global collaborative effort involving multiple space agencies including NASA, Roscosmos, ESA, JAXA, and CSA. With a lifetime cost exceeding $150 billion, the ISS was developed through a phased approach, initially launching key modules and progressively expanding the station's capabilities. The ISS serves as a microgravity research laboratory where scientific experiments are conducted, and it has provided valuable insights into the effects of long-term space habitation on human health. The challenges of maintaining a sustainable human presence in space, including life support, radiation exposure, and psychological well-being, were addressed through innovative solutions, many of which inform current and future missions to Mars. 3. Mars Exploration Program 2000–present. NASA's Mars Exploration Program encompasses a series of missions aimed at exploring the Martian surface, atmosphere, and potential for human colonization. This program has included numerous rovers, landers, and orbiters such as the Mars Science Laboratory Curiosity and the Perseverance rover. The total budget for the Mars Exploration Program has exceeded $20 billion. The program has followed a phased approach, initially focusing on robotic exploration to gather data about Martian resources, climate, and geology, which will inform future human missions. The challenges encountered, such as harsh environmental conditions and the need for in-situ resource utilization, are similar to those outlined in NASA's current Mars colonization strategy. The ongoing research and technological advancements from these missions contribute to the broader goal of establishing a sustainable human presence on Mars. NASA's blueprint for Mars colonization includes an ambitious 5-phase strategy with a budget of approximately $30 billion aimed at establishing a sustainable human presence on Mars by 2032. This strategy responds to various challenges posed by Mars's environment, such as radiation exposure, extreme temperatures, and resource scarcity, while promoting technological innovation and economic viability. Budget allocation and phases. 1. Phase 1, Unmanned Missions 2024 to 2026. Focus on sending robotic missions to conduct resource assessments and technology tests. Initial exploration of Martian soil and atmosphere to identify potential resources for life support in construction such as water ice and regolith. 2. Phase 2, Short-Term Manned Missions 2027 to 2029. Deploy astronauts for brief missions to test life support systems and gather real-time data on human health and Martian conditions. Initial setup of temporary habitats to evaluate the practicality of long-duration stays. 3. Phase 3, Infrastructure Development 2030 to 2032. Establish sustainable settlements that utilize in-situ resources. Development of Martian concrete using local materials to construct durable habitats. Begin implementing agricultural systems using aeroponics and algae bioreactors to produce food. 4. Phase 4, Expansion of Human Presence. Gradual increase in crew size and mission frequency. Focusing on building a self-sustaining colony. Further exploration of Martian resources and potential for local manufacturing. 5. Phase 5, Long-Term Habitation and Self-Sufficiency. Finalize the establishment of a permanent human settlement capable of supporting a growing population. Continuous advancements in life support and health monitoring systems to ensure the well-being of inhabitants. Challenges and solutions. Radiation exposure. Astronauts could receive significant radiation doses, necessitating the development of effective shielding methods. Proposed solutions include burying habitats under Martian soil or utilizing Martian concrete to mitigate exposure. Life support systems. The thin Martian atmosphere and extreme temperatures require innovative solutions. Aeroponics systems and algae bioreactors are highlighted as key technologies to support food production and oxygen generation. Psychological and physiological factors. Addressing the potential mental health issues and physical effects of low gravity and isolation is critical. Research into creating communal living spaces and recreational activities could help mitigate these effects. Economic viability and resource utilization. In-situ resource utilization ISRU, utilizing local materials such as water ice for drinking and hydrogen production is essential for reducing reliance on Earth-based supplies. This approach can significantly lower mission costs and enhance sustainability. Reusable rocket technology, emphasizing the use of reusable launch systems, will allow for more frequent and cost-effective missions, thus facilitating the ongoing supply of resources and personnel to Mars. Future outlook and predictions. By 2032, if NASA's plan is executed successfully, we could see the establishment of a semi-permanent human presence on Mars. This would mark a significant milestone in human exploration and could pave the way for further exploration of the solar system, including missions to the Moon and beyond. 1. Technological advancements. Continuous innovation in robotics, materials science, and life support systems will be critical. Research and development in areas such as artificial intelligence and automation may further enhance mission efficiency and safety. 2. International collaboration. As the vision for Mars colonization progresses, collaboration among international space agencies and private corporations may become more prevalent. Sharing technology resources and expertise could lead to accelerated advancements in space exploration. 3. public and private investment, increased interest from private entities in space travel and colonization could lead to additional funding and resources expediting the development of necessary technologies and infrastructure. For cultural and ethical considerations, as humanity expands beyond Earth, there will be growing discussions around the ethical implications of colonization, the potential for contamination of Martian ecosystems, and the rights of future Martian inhabitants. 5. Expansion beyond Mars. Successful colonization of Mars could serve as a blueprint for future missions to other celestial bodies such as asteroids or moons of Jupiter and Saturn, further expanding human presence in the solar system. Conclusion. NASA's comprehensive strategy for Mars colonization presents a bold vision for humanity's future in space. The phased approach, combined with innovative technological solutions and a focus on sustainability, has the potential to not only establish a human presence on Mars but also to inspire generations to explore beyond our home planet. As we move closer to realizing this vision, collaboration, investment, and continued research will play crucial roles in overcoming the challenges ahead.